The purpose of this short video is to highlight the key parameters in a newly introduced component as part of the Free Space Optics library, the Unmanned Aerial Vehicle channel. So UAV FSO channels can be modeled using this component. So let's go over some of the main features. The main tab, you can select the UAV role, whether the UAV is a transmitter or receiver, or both, for example. This has particular implications on the modeling of the mechanical vibrations at the transmitter or receiver platforms, which is only manifest for the UAV end of the link. The range is the vertical, the slanted range between the transmitter and receiver, which is 6 kilometers. And we can select the atmospheric attenuation, whether it could be user-defined or calculated from the FSO weather, which is from the FSO weather tab here. And you can select, of course, the beam waist for the transmitter beam, whether it's 50 millimeters is typical value in this configuration, or you can select, for example, based on the divergence angle of your beam, and you can calculate from there your actual beam waist at the transmitter end. You can determine the height of the receiver. Let's say this is a UAV that's present at 500 meters above the ground, and the transmitter is 50 meters above the ground. And you have the pointing error angles, and some additional parameters related to efficiency for both transmitter and receiver telescopes. You could also disable the telescope for the transmitter side, and you can disable the telescope for the receiver side. Now, this enables you to utilize the component as a free space propagation channel only, without giving due consideration to the telescopes at both transmitter and receiver ends. In the scintillation, you have the option of determining what the wavefront is, whether it's planar or spherical, and you can apply temporal scintillation with either log normal or gamma-gamma distributions. Furthermore, you could set the fright parameter, whether it's a user-defined fright parameter, and that's used for the generation of the turbulence phase screens in subsequent tabs. You could also calculate it from the index of refractive structure. So the CN square could be defined as a single value, or it could be uploaded from an altitude profile, which you can upload as a .data file, or a change or variation in terms of the Z, which is the slanted path of transmission. You could also use a altitude model, and there's a variety of altitude models you can select from HVP to clear, fried, and SLC day and night, for example. And once the CN square is determined, it has manifestations in the scintillation model and also an effect on the spatial turbulence. And under the spatial turbulence, you have an option of turning it on or off, and you have the Komoglove or the modified von Kerman. And you also have an ability to upload your own phase screen file, for example. And in this case, you can upload your own phase screen that's applied during the turbulence region, which is defined by an initial Z position for turbulence and a final Z position for turbulence. You also have an ability to turn on the effect of beam wandering. This could be applied for the full link or over the region of turbulence only. And in the UAV dynamics, you could turn it on, and in doing so, you have a mechanical jitter for the UAV at the transmitter side. You can also control the mechanical jitter of the receiver side, and a common angular, regular angular tilt involved for both transmitter and receiver. So that highlights primarily the main parameters inside the component. If we want to have a look at some of the results in the component, some of the results for the components, we have the beam waist at the transmitter end. There is the beam divergence angle, the beam waist at the receiver end, and you have the particular losses, whether the free space path loss and geometric loss, for example, and you have the transmitter pointing errors. You also have an ability to check to see the turbulence, receiver turbulence aperture capture loss, the due to turbulence, due to the dynamics, and due to the beam wandering, and a total capture loss. And you also have the total channel loss, the values for the fright parameter, index of refractive structure, and some rate of parameters in alpha and beta sigma. These are related to scintillation. You also have displacements in the beam wandering displacements for the spatial mode, and displacements due to jitter, and finally the total displacement. And if you can have a look here at the output, you can see here that if we have a look at the output mode, this is an example of a distorted beam, spatial beam, that's shifted and also distorted. In addition, you can also check in the component to see, for example, what are the various plots you can obtain here. For example, we can see this index of refractive structure versus transmission distance, Cn square. We also have the beam evolution versus Z position, which is transmission distance. We have the Cn square versus altitude, for example, between 550 to 500. And we also have the commutative fright parameter and the value of the horizontal fright parameter. In addition, we also have the receiver aperture, which is the receiver capture area, and we also have the received spot size. You can sense from this the amount of overlap between the receiver aperture location and the beam that's been shifted and affected by the transmission.